All right, everyone. Welcome to the last week of the semester. I guess not counting finals week. Last week of classes. So before we get going here, I just have a few announcements. So some of you may have seen your grades be adjusted like marginally this like sometime today. It's because I realized that on Canvas, it wasn't weighting exam 3 the same as the other exams because exam 3 was out of 93 points, but the other exams were out of 100. So it was weighting the other exams slightly more than exam 3. So the way I fixed that was I put exams 1 and 2 in their own section, and that was worth 30%. And then I put exam 3 in its own section, that was worth 15%. That fixed the issue. It shouldn't have affected your grade too much unless you got like a drastically lower high score on exam 3. Is that how that works? It shouldn't have affected your grade too much, but I just fixed that so all the exams are weighted equally. So that's what happened if you were looking earlier today. Also, I posted some homeworks on polar coordinates, and those will be due on Friday, and those will be excellent things to take a look at for studying for the final exam right here. All right, so with that being said, I think we're ready to go here. What I'm going to be doing today is I'm going to be going over the practice final that I've posted on Canvas. That's in the same place as all of the other practice exams under the old exam / non-grade assignment section. So I'm just going to be going over that today. And then if we don't get it finished today, which we probably won't, we'll go ahead and finish tomorrow, and then I will answer any general questions that you guys have. All right, so let's go ahead and get started. So question 1 here. So this is the practice final. All right, so question 1. Question 1 is just asking us to do an integral. So let's see, what's the integral it's asking us to do? It's the integral from -infinity to 0 of x squared e to the x dx right here. All right, so let's go ahead and do this. So remember, this is an improper integral because it has a -infinity in here. So this is going to be the limit as r goes to -infinity of the integral from r to 0 of x squared e to the x dx. That's how we deal with integrals that have infinity on the bounds, or that's how we deal with integrals that have maybe like an undefined number that would be like dividing by 0 or something like that in here. So we just have the limit as we approach that number right here. All right, and then once we have that limit, all we need to do is we just need to do the integral normally and then just worry about the limit at the end. So do you guys remember how we would do this integral? How do we do this one? X squared e to the x. Yeah, integration by parts or the tabular method. That's right. So I'm going to have my derivative column and my integral column. I'm going to put x squared in my derivative column, and I almost always choose to put the polynomial in the derivative column, except for maybe if there's like a log or some weird function here. And I have e to the x here. So I have 2x, and I have 2, and then 0. And we have e to the x, e to the x, e to the x. We connect these diagonally downward, and then we alternate sign. All right, so what is this saying? This is saying that our integral is going to evaluate to, now since all of these will be multiplied by e to the x, I'm just going to factor out e to the x from the answer. So what I mean by that, this is going to be x squared minus 2x plus 2, all of that times e to the x. Because if I distributed it among these three, then it would just be e to the x multiplied by each of these right here. All right, and then remember, this is going from r to 0 right here. Is the practice exam similar difficulty as the final? Practice exam is probably harder. Actually, practice exam is definitely harder this time. But that means it's good practice, because if you do the practice exam, then you'll be in good shape for the final. All right, and then finally, let's go ahead and plug in our bounds here. So I plug in 0, and I have 0 minus 0 plus 2, and then e to the 0 is 1. So I have 2 when I put 0 in. Then I subtract and I have r minus 2r plus 2 e to the r. And we also have the limit as r goes to negative infinity. I almost forgot that. Okay, so now we just have a 2 here, but the real concern is what's happening. Oh, this is r squared. Oops. The real concern is what's happening with this right here. So remember, when it comes to limits going to infinity, exponentials have a higher priority than polynomials, right? What the exponential does is going to dictate what happens as opposed to the polynomial. Now, as r goes to negative infinity, what is e to the r going to do? It's going to go to 0. That's right. And because exponentials are more powerful than polynomials, what this does is going to overwhelm what this is going to do. So this whole thing is going to go to 0 because e to the negative infinity is going to go to 0 right here. So I have 2 minus 0, and last I checked, that'll end up being 2. So that's going to be our answer for this one right here. So this is simultaneously a test on improper integrals as well as a little test on doing the tabular method right here. All right, so we got that one. Let's go on to number 2 here. I think I put these in order of the topics. So most of the first ones will be integral questions, and then we'll get on to series, and then finally parametric polar. All right, so this next question, find the antiderivative, so we're going to do an integral, of 8 secant cubed of x tangent squared of x. Okay, now let's see here. So this is a product of different trig functions, and we have a secant and tangent. Okay, so we have an odd power of secant and an even power of tangent. So was that one of the nice cases, or is this the one that like took forever? Yeah, this is the bad one. This is the frowny face one. Okay. Yeah, like I said, this is kind of trying to train you guys with harder problems here. So what I'm going to do is I'm just going to do the integral of secant cubed tangent squared, and then I'll stick the 8 in at the end, or at least make sure that there's an 8 right there. So I'm going to focus on just doing this. Okay. Now remember, the way we did this, the way we started off, is we turned all of the tangents into secants using the Pythagorean identity. So tangent squared is secant squared minus 1. And then if I were to distribute this, I get secant to the 5th minus secant cubed. And then that I can make into 2 different integrals. Okay. Now, why did I do that? Well, I know how to integrate secant cubed. That was the one that I specifically told you guys to remember because this one shows up often enough. It was half ln of secant plus tangent plus secant times tangent. So I know how to deal with this one. And then all I have to do is just get rid of this somehow, and then I could just put in the answer for this, and then I'm done. Okay, now remember what we did next. We did some of the stuff where we add copies of the integral to both sides. So remember that if we trace back our steps here, what we have right now is equal to the original integral, right? So it's equal to secant to the 5th, that's a 5, minus secant cubed. Now what I'm going to do with secant to the 5th is I'm going to do IBP. That's what we do on the high powers of secant. And the way I'm going to do IBP is I'm going to have u be secant cubed and dv be secant squared. And let's say I were like feeling really evil or something. I made this be like secant to the 7th or something instead. I would still put a secant squared here, and then I put a secant to the 5th here. So I always just put a secant squared here and then all of the rest of them over on the u. All right, and the reason why I do that is because I have to integrate whatever dv is, and the integral of secant squared is tangent. Now I'm going to use the chain rule to do the derivative of this. So I use the power rule. So I have 3 secant squared and then I multiply by the derivative of the inside, which is the derivative of secant. So I end up multiplying by another secant tangent. Okay, now I'm going to use the by parts formula. So let's see, I have u times v. So I have secant cubed times tangent. And then I subtract the integral of v du. So I have the integral, or rather 3, because of the 3 here. And then I have secant cubed, because of secant times secant squared. And then I have tangent. And so that was what happened to secant to the 5th. And then remember, the secant cubed is kind of just hanging out here in the back. Okay. Now, why did I do that? It looks like I just made more terms here. I made this messier looking, but there is something good that's going to come out of this. What can I do now? Wrap around. That's right. Because notice that this integral is the same as this one. So what I'm going to do is I'm going to add 3 copies of this integral to both sides. And that will cancel it out right here. And I have 1 of these integrals plus 3 of them will make 4 of them. So 4 times the integral of secant cubed tangent squared is secant cubed tangent minus integral of secant cubed. All right, now we did what we said we were going to do. We got rid of that integral of secant to the 5th. So now all we need to do is just replace this with the thing that we hopefully memorized earlier. But even if we happen to forget what this is, we could also do integration by parts on this, with secant squared being dv and secant being u. But in all honesty, it's easier to memorize this one. All right, so remember the integral of this is 1/2 times the integral of secant, which is log of secant plus tangent. And then we add the derivative of secant, which is this right here. Okay, then we're almost done here. We have 4 times this integral, but what was the original problem? We wanted 8 times that stuff. So how are we going to get that? We'll just multiply both sides of this by 2, and then we'll have the right coefficient here. So 8 times the integral, which is what we wanted, is 2 secant cubed tangent. And the nice thing about multiplying by 2 is it cancels out with this 1/2. So I have minus ln of secant plus tangent. And if I distribute the negative sign here, I have secant times tangent. We're done with our integral, so we can put our plus c at the end there. All right, so there we go. So that's about as bad as trig integrals can get. This is like the worst of the bunch. And this is how we do it. So if you do this one, in all likelihood, you could probably do the other ones as well. All right, the next one is another integral. Yeah, what's up? Yeah. Okay, all right. All right, someone's just copying down something. All right, question 3. It's another integral. This is the integral of arctan of the square root of x squared minus 1. Okay. Now, this is an integral of just one kind of strange function on its own, right? So what method do we usually use in that scenario? Yeah, integration by parts, right? So we're going to do integration by parts here. Trig sub is technically possible, but there's like a really weird like subtlety that happens with the trig sub here. So I'm going to go with IBP for this. But trig sub's not wrong, because we could do x equals secant. All right, but I'm going to do integration by parts. Let's see what happens with that. So u will be arctan of the square root of x squared minus 1, because that's all we have here. And then dv will be dx. All right, so then that means the du will be the derivative of this. So the derivative of arctangent is 1 over 1 plus the inside squared. Now the inside squared will actually just be x squared minus 1 because I'm squaring this square root right here. And then I multiply by the derivative of my inside. So the derivative of my inside, if I end up doing the derivative of this, I end up with x over 2, or sorry, no, the 2's not there, x squared minus 1, if I do the chain rule again on this here. And then v will be x. Okay, we could definitely clean up some of the stuff here with this nasty derivative. So we have 1 plus x squared minus 1, so those 1's will go away. I think I'll save the rest for later. All right, so then what do we get when we do the by parts formula? We have x arctan of root x squared minus 1. And then we subtract the integral of v du. So we have x times x is x squared. And then on the bottom, we have x squared square root of x squared minus 1 right here. All right, so that's pretty convenient because those can cancel out. What was that? Oh, right here. That went. So this, why does 2 go away? So we did the power rule. We bring the 1/2 down here, which would create the 2. But then the derivative of the inside of this would be 2x, and then we would have the 2 on the top right there. So that's why this 2 ended up going away. All right. So now we're just left with this integral, the integral of 1 over the square root of x squared minus 1. Now this is something that we should probably do trig sub on here. So what I'm going to do, so I have a variable squared minus a number squared. That says to me that I'm going to use secant of theta. So I'm going to use x equals secant of theta, no coefficient necessary because that's just a 1. So let's see, dx will be secant of theta, tangent of theta, d theta. Okay, so I have this stuff here, which is honestly just going to float along for the rest of the problem. And then I subtract, let's see, dx is the secant tangent I just got. And then on the bottom here, I have the square root of x squared, or secant squared, minus 1. Okay, now what is the denominator going to simplify to? We've seen this quite a bit in trig sub. What is the denominator going to turn into? Yeah. Well, yeah, so inside the square root will be tangent squared, and then we do the square root, and we actually just get tangent. So this is going to turn into tangent of theta right here. Now that's very convenient because if this is tangent of theta, it will cancel with the tangent of theta up there. So what we're really doing is we're just integrating secant of theta d theta right here. All right, now let's try to remember what the integral of secant is. Well, I guess we kind of used it in the last problem in remembering the secant cubed thing. The integral of secant cubed, or sorry, of secant is ln of absolute value of secant of theta plus tangent of theta. All right, and then all it's left to do right now is to just convert back into x's. We're going to convert this back to x's, and then we're finished here. Okay, well, we know how to convert secant back. Secant is just x. So we're just going to put it in x for that. Okay, no problem there. All right, now tangent. Tangent, we're going to have to use the triangle to get here. So let me kind of draw the triangle over here. Okay, so we have x over 1 here. All right, it's been a while since we've done this. Secant of theta is going to be what over what? Anyone remember that one? That's right. It's going to be hypotenuse over a j. Oh, what am I writing that there for? been a long time since I've done it too. Yeah, we have hypotenuse over adjacent. That's right. So my x is going to go in the hypotenuse slot. 1 is going to go on the adjacent. And then when I use the Pythagorean theorem, long story short, I'm going to have the square root of x squared minus 1 over here. And remember, that's a good sign because we want it to show up in our original integral, and it does. So tangent is opposite over adjacent, right? Meaning that we have square root of x squared minus 1 over 1, or just root x squared minus 1. So that will give us the rest of this here. There we go. There is our antiderivative. Now, technically, we could have tried to use trig sub in the beginning. We could have done the x equals secant of theta back there. And that actually would have been pretty slick because then we would have had arctangent of tangent of theta. But the trick with that is that arctan of tangent of theta in many cases will actually just be absolute value of theta. So you would have ended up with something really weird here. You would have ended up with arc secant of absolute value of x right there. So you would have had to be kind of very careful about how you did trig sub for that. So this one's honestly, you see like arctan of something, it's honestly best to do IBP. All right, so there we go. It was a good integral. Okay, the next one's a really good question. Let's take a look at that. Okay, question 4. All right, question 4 wants us to compute another integral. So it wants us to find 1 over x squared times x squared plus 1. All right, so it wants us to do that. Okay, now there are going to be 2 ways of doing this integral. What's one way of doing this integral? What was the way we dealt with rational functions? Yeah, we're going to use partial fractions. That's right. So we could use partial fractions to do this. So I'm just going to go ahead and do it that way first, and then I'll show you kind of a cool trick to make this be a lot easier. Or do you guys just want to see the cool trick and not do partial fractions? Now let's just both do a kick flip. Yeah, sorry, I can't do that. All right, I'm just going to do partial. I'll just do both of them. So I'm going to do partial fractions. All right, so what is the partial fraction decomposition of this? It's going to be a over x plus b over x squared, because remember, when we have x to a power, we have 1 copy for each x. And then this is an irreducible quadratic. So we have cx plus d over x squared plus 1 right here. All right, now let's see here. So remember, there are a few different ways of getting these coefficients, one of which was cover up, and that was probably the nicest one to use. Now, unfortunately, we can only use cover up for b right here, because b has the highest power of something that could be set equal to 0 here, because there's nothing that will make this 0, at least nothing real. 0 will make these 0, but we can only take the highest power. So we could use cover up for b. Okay, so I cover up the x squared, the thing that it shares, and I plug in 0 into here. So I have 1 over 0 squared plus 1, giving me that b is going to equal 1 right here. All right, now that that's out of the way, usually the best way of finding the coefficients when we have irreducible quadratics is to multiply by the denominator or clear the denominators and then compare both sides. So I'm going to multiply both sides by x squared times x squared plus 1. Now, when I do that, I cancel with the denominator here, so I have just 1. When I do that here, I have ax times x squared plus 1. When I multiply that here, the x squareds cancel, and I have b times x squared plus 1. And then when I multiply here, the x squared plus 1s cancel, and I have cx cubed plus dx squared right here. All right, now let's FOIL this out. I have ax cubed plus ax plus bx squared plus b plus cx cubed plus dx squared. All right, so we FOIL that out. And then if we combine like terms together, well, I have some cubes here. So I got those. I have b plus dx squared. Okay, that's all well and good. And then I have ax, and then our last coefficient, which is b. Okay, so now I'm going to use the comparing polynomials method. So even though it doesn't really seem like it, 1 is technically a polynomial. It's a constant polynomial. Now, it doesn't have any x's here, so we can kind of imagine those as like 0x, 0x squared, 0x cubed. Now, in order for this polynomial to be the same as this one, their matching powers of x need to have the same coefficient. So this has got to be 0. So does this, and then this is the constant term, which has got to be 1. We already knew that. We already knew b was going to be 1. But some new information we get is that a is 0. So we now know that a equals 0 from this. Next, we know that b plus d is 0. But we already know that b is 1. So that implies that d has to be -1 right here. And then finally, the only one we don't know is c. What is c going to end up equaling? It's going to be 0. That's right, because a plus c is 0. But the thing is, a was already 0. So c is going to end up being 0 here. Okay, so let's go back to where we started here. We have this form for our partial fractions, and now we know the coefficients. So that also means that we can rewrite our integral as the integral of 0 over x, so a was 0, b was 1, so it's 1 over x squared. And then we have c being 0, and then d is -1. So actually, this is a minus. Okay, and thankfully, these are both pretty easy integrals to do. This is technically x to the -2, right? So if I do the power rule on this, I raise the power to be -1 and then divide by -1. So I have -1 over x, or -x to -1. And then what is the integral of this right here? This is an important one I told you to remember. That's going to be arctangent. That's right. There we go. There's our integral. All right, so that was the longer way of doing it. And there's nothing wrong with doing it this way. This is a totally fine way of doing it. But there is something nice that we could have done in the beginning. So there's a little bit of a trick for this one. So in a few of the problems in the integration section, I think they were mostly trig subproblems. We had to add and subtract the same thing on the top, right? And that we could do that because that's equivalent to adding 0. Now, we could do the same thing here, and it'll end up making this integral way easier. What I'm going to do is I'm going to add and subtract x squared. How do I want to write this? I want to write this as -x squared plus x squared plus 1 over x squared and then x squared plus 1. So you could do this with functions or variables too. It doesn't only work with numbers. You can also do it with x's. Now, why did I do this? What I'm going to do is I'm going to split the fraction up. So I'm going to have this over the denominator, and then I'm going to have this over the denominator. So I have -x squared over x squared times x squared plus 1. And then I'm going to have x squared plus 1 over x squared times x squared plus 1. Okay, now why did I do that? Well, these can cancel. And I just have -1 over x squared plus 1. And then these can cancel. And I have 1 over x squared. And I instantly jumped to this step right here. So if you ever see that your numerator almost looks like one of the things on the bottom, consider adding and subtracting the missing piece to the numerator, because you might be able to get away with doing something like this right here. So this was kind of a shortcut for this one, and we skipped doing partial fractions. Can we do IBP on this one? Ooh, that's an interesting prospect. I don't think it would work well on this one. I think dv would have to be 1 over x squared plus 1. I'll give you v is arctan. Yeah, I don't think IBP would have worked out on this one, unfortunately. Okay, how does b plus d equal c? Oh, it's a 0. Sorry, I just didn't close the 0. There we go. Although c is 0, so technically that would have been true coincidentally. All right. That was question 4. There's 2 ways of doing that one. Let's go to question 5. Okay, so this one, so we're done with just the pure integrals. Now this one's starting to get from the application section here. So this one is about finding the volume of the shape created by rotating the region between, what is it? X equals 0, y equals cosine of x, y equals negative cosine of x, and then x equals pi over 2. Around the x or y-axis. That makes a difference, y-axis. Okay, now the first thing we should do with any of these volume and revolution problems is we should draw the picture. It's immensely helpful to draw the picture for these. All right, so here are my axes. I know x equals 0 is going to be one of the boundaries here. I'm kind of shade that in a little more. I have y equals cosine of x. So cosine is the function that starts at the point 0, 1, and then goes downwards from there. So I have that. And then I also have y as negative cosine of x, which will start at negative 1 and go up. And these two will end up meeting right here. And what point will both of these be 0? It'll actually be this last coordinate here. X is pi over 2. So what we're doing is we're taking all the volume in this, or the area in this, excuse me, and we're spinning it around the y-axis right here. Okay, now remember there were 4 different situations for these volumes of revolution problems. There was where we had functions of x going around the x-axis, functions of x going around the y-axis, and then functions of y going around the x-axis, and functions of y going around the y-axis. Now in this one, we have functions of x, because x is like the independent variable that we're using in the formula. So this is functions of x, and we're going around the y-axis. So I like to think of that one as opposing variables. We have function of x around the y-axis. Yeah, so then Sean has it right here. It's going to be the shell method. So we're going to use shell method for this. All right, so the shell method, the volume is going to be 2 pi times the integral from a to b. Now a is our lowest x value, which is 0. B is our highest x value that we get to, which is pi over 2. And then the formula goes, we have an extra x in there no matter what. And then we have the function with higher values, so that's cosine, minus the function with more negative values or lower values. So it's going to be negative cosine. So this is going to be our integral right here. So opposing variables means you should use the shell method. That's right. And then matching variables means you should use washer. All right, now we could definitely simplify this because we're subtracting a negative, right? So this will be 2 pi times the integral from 0 to pi halves of 2x cosine of x. All right. So here, now we're going to do this integral, and this is an integration by parts. Okay, so this is 2x, and we have 2, 0. We have cosine of x, sine of x, and negative cosine of x. Okay, this is positive, this is negative. So we have the 2 pi that was out in front of all of this, and then we have 2x sine of x. And then plus 2 cosine of x. And this goes from 0 to pi over 2. Okay, now we just need to plug in the numbers. Let's see what happens when we plug in these numbers. I plug pi over 2 into here. Sine of pi over 2 is 1, and then pi over 2 times 2 is going to be pi. So I have pi there. What's next? I plug pi over 2 into cosine, I get 0. Okay, and then I plug 0 into here, I get 0. Then I plug 0 into here, and I get 2. But I'm subtracting because it's the bottom bound, remember? So this is minus 2. So I end up getting 2 pi times pi minus 2 right here. So use tabular for trig and e to the x. You should use tabular for sine or cosine times a polynomial, or e to the x times polynomial. Yeah, that's right. Now remember, one little way we could kind of check our answer here to make sure it at least has a chance of being correct is that this is the volume of something, right? So this has got to be positive. So 2 pi is positive, and then pi is bigger than 2. So this is positive. If we got like 2 minus pi or something like that, then we would know something is wrong here. And since a lot of this stuff is multiple choice, if you see a negative answer, you can immediately eliminate that one as a possibility. If you're like pressed for time, you got to guess or something. Yeah. Someone asked how long the exam is going to be. It's going to be 2 hours. It's good. I think it's from 12:30 to 2:30 on April 26th, which is a week from today. Have the exam scores be released? Yeah, pretty much. I haven't withheld any so far. All right. Let's see here. Question 6. All right, this is one of the dreaded physics problems here. Okay. Let's see. Compute the amount of work it takes to pump all the water out of an inverted square pyramid. So what do I mean by that? It's a pyramid, but it's going to be upside down. So it's going to be looking like that. Okay, so inverted square pyramid. And then what are the dimensions of this? Of height 4 and base length 2. That is filled to a height of 1 with water. And this problem, it says also ignore rho and g right here. So even though rho and g are part of the physics of this, we don't really care about that in this class. We just want to focus on being able to set up an integral and actually do it. I'll let someone else have you memorize what these are for various things. All right. So let's see here. So let's draw a little bit of a better picture than this. That's well, whatever. Okay, so this thing has a height of 4. It has a base length of 2 right here. And the water goes up to a height of 1. So only like the little corner at the bottom is effectively going to be filled with water here, because this only goes up a height of 1. Okay, so we need to figure out how much work it's going to take to get the water down here up and over the top right here. Okay, so let's see here. Let's go ahead and set this up. So we're computing work, right? So we're going to do the work on one little slice of the water. So remember how we did this? We broke this up into these tiny little rectangular slices. Now the work on one of the slices is force times distance, right? So let's look at the force here. So the force that we're fighting against to get all of the water up to the top is gravity. And gravity has the force mg. Okay, g is a constant. In fact, we could just get rid of it now if we want. So this is going to be m times d. Mass is going to be density times volume. So this is rho v d right here. And we could ignore rho too, so I'm going to get rid of it. Now the volume here, the volume is talking about one little rectangular slice of water. So I'm going to call the volume of this, I'm going to say its side lengths are L for length. So we have L squared as the side lengths. And then what do you think I'm going to call the height of this very thin, teeny little rectangle here? What do we usually call this? That's right, it's going to be dh. And that means I'm going to call the variable going up and down h. So it's L squared dh. And then we still haven't done the distance yet. Okay, so what I'm going to do is I'm going to define h equals 0 down here. And then I'm going to make it increase upwards. So this is a height of 0. This would be a height of 1. And then when we get to the top, that's a height of 4, right? So then what is the distance that we need to move each piece of water? Well, let's see. So if we're at a height of 1, how much further up do we need to move the water here? If we're at a height of 1, how far do we need to move it? We need to move it 3, right? And then if we're all the way down here at 0, so d of 1 is 3. If we're down here all the way at h equals 0, then what is the distance we need to move up now? It's going to be 4 right here. So it seems like the bigger that our h is, the smaller our distance we need to move up is, because we already moved up some of it by being higher. So this means that our distance is going to be 4 minus h. If we're all the way down at the very tip of the pyramid at height h equals 0, we have to move it up 4. But if we're up a little bit ways and we're up at h equals 1, then we have to move it less distance. And the bigger h gets, the less we have to move it. So when we go up to 1 here, we have 4 minus 1 is 3 right here. So this is going to be what we're going to put for our distance here. Okay, so that's what d is. Okay, so we got that part. Now we need to get what L is. So remember, L is the length of the sides of these little boxes. Now, do you guys remember how we did that? We did a few things like this in a few different problems. What was the geometric thing that we used to turn L into H? That's right, it's going to be similar triangles. So if we take a side view of this, it's going to be a triangle. Let's say that our thin little box of water is right here. So remember, this length is h. The total length of the pyramid, or the height, is 4. This is 2. And then this is L right here. Okay, so by using similar triangles, the big overall triangle is similar to the tiny little triangle wedged into the corner here. So if I do 4 over 2, or vertical over horizontal, I'm going to get the same thing if I do it this way. I'm going to do vertical over horizontal. All right, well, last I checked, 4 over 2 is 2, and then I multiply up the L. H is 2L, or in other words, H over 2 is L. Oops, I'll move this up a bit. All right, so H over 2 is L. I'm going to put that here. Now I'm squaring it, so I'm squaring this. So I'm going to have H squared over 4. Okay. Now this is good because I have all the same variable and I know the work on one slice. Now the way all these problems went is that when I found it on one slice, I just throw it into an integral and get all the slices. So this is going to be the integral of H squared over 4 times 4 minus H. And remember, I defined h equals 0 to be at the bottom, and then it's going to be 1 at the top of this water here. Now, the bounds of the integral is always where the object is that we're moving. So our object starts down here at h equals 0, and it goes all the way up until h equals 1. So this one will be the integral from 0 to 1 here. If I did something like define h equals 0 at the top, like I've done for some other problems, then this integral would have went from 3 to 4 if I were to define h equals 0 up here. But it's actually a little bit easier in this problem to do h equals 0 down here. All right, and then we have ourselves a nice little polynomial integral to do. I'm going to move the 1/4 out. And then I have 4h squared minus h cubed. And then I integrate. So I have 4/3 h, oops, I already did the integral. 4/3 h cubed minus h to the 4th over 4, 0 to 1. So this is 1/4. And then we have 4/3 minus 1/4. I guess if we combine the fractions, what is that going to be? 16 minus this will be 13 over 12. This will end up being 13 over 48 right here. So there we go. So that was kind of a review on one of these physics problems right here. Now, there are other ways to do this problem too. Like I was saying earlier, you could have defined h equals 0 to be up here. And then this part would have been different. This would have been a little different too. And your integral would have went from 3 to 4. Now, I tried doing it that way. That way is like a lot more arithmetic heavy. So I don't think you want to do it that way. I think h equals 0 at the bottom for this one is certainly better. Yeah, what's up?
Sorry, why aren't the bounds from 1 to 4 instead of 0?
Because it's only, so why are the bounds not from 1 to 4 instead of 0 to 1? The bounds are always wherever the object we're moving is. So we're moving the water, right? So the water starts at h equals 0, and then the water ends at h equals 1. So it's only where the object we're moving begins. Why is the object from 0 to 1? Oh, I just explained that. Okay, good. We have 2 birds with 1 stone with that. All right. Do we have enough time for another question? Ooh, we only got 2 minutes. Let's see here. Yeah, I'll just go for it. This one's not going to take long. So this one's about sequences. So which sequences converge? Okay. So my first one is ln of 2n plus 1 minus ln of 2n minus 1. Now, the key word for this is that these are sequences, right? How do I know if a sequence converges? There's only one way to really tell that. Yeah, you just do the limit as n goes to infinity. So if we're just looking at a sequence, we just look at the limit as n goes to infinity. Now, before I do that, I'm going to combine this using log rules. Even though they seem kind of weird and annoying, log rules are actually your friends. They're going to help you do this. So this is another way of writing it. And then the limit as n goes to infinity of this. Well, let's see. The inside is going to 1, right? So this is ln of 1, which is 0 right here. So this does converge, and it's going to converge to 0. All right. The next one is an is going to be 9 to the n over e to the 2n. Okay, so another way of thinking about this one is this is 9 to the n over e squared to the n, right? Now, I have no idea specifically what number e squared is, but I know that e itself is less than 3, right? That means, by that reasoning, that e squared's got to be less than 9. So this number, e squared, is a smaller number than 9. Now, if we have a bigger number to the n over a smaller number to the n, this is going to go to infinity. So this one's going to diverge here because e squared is less than 9. Okay, and next one here, Cn is 1 over n. This one's trying to trick you to think about series because we know the series for 1 over n diverges. But as a sequence, the limit as n goes to infinity of 1 over n is 0. So this does converge. So as a sequence, 1 over n is fine, it converges to 0. But if I put a sigma here and I asked if that converged, that would be false. All right, next one. Then we have one more. Negative 1 to the n plus 1 over n. Okay, what's this one going to do here? Well, if I look at the limit as n goes to infinity for this one, I know this part's going to 0, right? But then what's this doing? It's just flipping back and forth between -1 and 1. And as the influence of this wanes over time, this is just going to focus on this part right here. So this is just going to keep flipping between a number close to 1 and a number close to -1, and it's not going to settle down. So the limit of this does not exist, meaning that the sequence diverges right here, because this guy can't decide how he wants to settle down. And then finally, I have f sub n. I didn't want to use e because that's a number. I have 1 plus 1 over n to the n. Okay, we've seen this before. What is this sequence going to go to? You guys remember what this is going to be? Yeah, it's just going to go to e. That's right, because the limit as n goes to infinity of 1 plus 1 over n to the n equals e. So this will converge. All right, there we go. So there was our sequence question right here. All right, that's about all the time we have for now. I think the next few questions will go a bit quicker, so I think we'll probably be able to finish this exam next class here. All right, that's it for today. So I will see you guys on Wednesday.